Hello, my name is Brian O'Malley and I'm a master's degree student at Full Sail University. I've recently been doing a project where I've been trying to teach Go to neural networks for use on mobile devices. One problem that I ran into was there's not a lot of really good guides, even for someone who's a trained computer programmer, to really get into neural networks. There's a lot that go very in-depth into the math behind them, and there's a lot that really just only scratch the surface as to the general use cases for them. But there aren't a lot out there that really describe the architecture and how to implement your own neural network. So that's what I'm going to be going into. So I'll be presenting my programmer's guide to neural networks. The first thing that I'll be going through is just the general overview of what a neural network is, the use cases for them, the general mechanisms behind them, how you architect them and determine what metavariables you're going to use, how the math comes together, and finally, how to train your own neural network. So what is a neural network? These were originally inspired by biological nervous systems in the 40s. They were proposed by researchers back then, both in terms of possible electronics projects, so just doing them in hardware, or possibly in software, but back then there wasn't really, all the math behind them wasn't figured out, and there wasn't really a lot of good solutions on how to make them work. Up until the 70s, when we discovered the backpropagation algorithm for neural networks, and it really became something that was a possibility of actually doing. This really didn't take off, though, because there were a lot of competing different theories on how we could best achieve this sort of machine learning until about the 2000s and the advent of the idea of deep learning. And deep learning is really where neural networks can shine compared to some of the other applications you'll see. Neural networks really started taking off and winning competitions in pattern recognition around 2009 to 2012, and that's when you saw bigger companies like Google and stuff like that really begin to become more interested in them. So some of the use cases and purpose of neural networks are classification, where you basically take a neural network and train it to understand the difference between different types of data. So you might teach it to, as the example on screen here is trying to do with MATLAB, teach it to understand the differences between images of drawn handwritten digits. This is trained off the MNIST data set. This was a prototype that I did for my project. And it basically takes single handwritten digits of a certain size, 0 through 9, and takes those bitmaps and tries to determine what digit it is. And it can actually get very, very accurate. They're pretty impressive. You also have autoencoders, where you basically take a neural network and you teach it how to boil down a data set into a smaller approximation of that data set, and then how to reconstruct that back into a full approximation of the original data set. And if it gets very, very good at this, you can get very close to lossless encryption with this. And depending on how well your network is formed and trained, you can actually get some pretty good, not encryption, compression with these. So these are things that companies like Netflix or stuff like that might be very interested in, because you can sort of get custom tailored compression algorithms depending on what type of data. So for example, you might be able to train a neural network to get the best possible compression on season 1 of House of Cards, and it'll beat everything else that's trying to compress that, best case scenario. You might also have functional approximations, where you're taking a large system of variables and trying to determine an output value based on that variable. One example that's used in a lot of tutorials on neural networks is the idea of estimating the cost of a house based on a set of variables about that house, like number of rooms, number of bathrooms, square footage, what type of neighborhood it's in, proximity to schools, stuff like that. So you feed all that in, and out the other end, the network, after being trained, spits you out an approximation of the house's sale value. Another thing you'll see neural networks used for is forecasting. So you might say, take the last 6 months of the performance of a given stock, and then give that to a network that's been trained on history of different stocks that are similar to the one you're trying to predict, and it'll give you a forecast of the next 3 weeks of values for that stock or something like that. And depending on how good your data set was leading up and how well you've trained your network, it might give you a fairly accurate forecast, barring any sort of weird real-world chaos. Another more advanced application of neural networks would be clustering, which is taking a data set and portioning it off into similar groups of data. That's a bit more of a complex, more advanced use case for neural networks, though. So the general mechanism of neural networks, one of the easiest ways to go through this is the terminology. So you're going to have different layer types in a neural network. You can have input, output, and hidden layers, which I've somewhat diagrammed here. So your input layer is just all your input values. So in your house example, each one of these nodes might be something like number of rooms, number of bedrooms, square footage of the house, et cetera, et cetera, et cetera. And then you're going to have this series of weights and possibly a bias value. So basically for each one of these inputs, you're going to take all of the inputs, multiply them by a specific weight that's been trained, add them all together, again, possibly with a bias value, and that's going to be one of your hidden layers values. Or if you're only using a one-layer network, this could just be your output layer. Usually one-layer networks aren't very common, though. You're going to have at least one hidden layer and possibly several. And the main difference between regular learning and deep learning is just the number and size of those layers. So in this case, you're going to take all your different inputs, multiply them by a weight, add them together. That's one value. Then you have another set of weights. You do it again. That's the next value, next. And as you train the network, these weights will sort of coalesce into approximating different things. And that's what we call an activation. So you might have one of these nodes that has a certain level of activation based on a certain subset of your variables. And you can sometimes discern a little bit of what the network is doing by looking at these trained weights and analyzing it for a certain input example. So you might find out, oh, well, this hidden value is weighted such that it lights up for whenever we have a high number of bedrooms and a high square footage and a high number of bathrooms. So this might be estimating something like overall size of the house, and then that'll eventually get fed into even more weights and contributes to the final cost approximation for that house. Or it might be completely inscrutable to you. That's one of the big downsides of neural networks, honestly, is that they're a little bit black box if you can't sort of figure out what's going on in there. One term you'll see used a lot is tensors. A tensor is a word that's used in several different contexts with somewhat completely different definitions. So tensors are used in geometry, in physics, to represent different sets of forces on an object. But in terms of neural networks, a tensor is basically just a structured set of variables. So that could be a vector, it could be a matrix, it could just be a list of scalar values. Most of the time when you see tensors used in conjunction with neural networks, it's going to be this set of weights here, which is usually going to be represented by a matrix. And you're going to use basically the same matrix math that you use in linear algebra, except you just might call it tensors instead. And the mechanisms by which this operates are called forward propagation and back propagation. What we've already explained so far, where these inputs are multiplied by weights, summed up together, and an activation occurs to generate a value for that hidden layer, and then we repeat that again for the next layer and the next until we get to the output. That's forward propagation. Back propagation is where you take that final output, compare it against what you thought it should have been, call that an error rating, and then you propagate that error backwards through the network to update all of your weights so that next time it gets the answer a little bit closer to what it should have been. So some of the architecture and metavariables that you're going to need to consider when putting together your own neural network is one of the first things you're going to see is whether or not you're going to use normalization. Normalization is basically just a mathematical way to penalize the network for using weights that are too large. That's going to help you avoid overfitting your network, which is something we'll get into when we talk about the training layer, but just know that overfitting is a bad thing. Normalization helps it. Dropout's a more advanced version of normalization, where instead of just penalizing large weights, what you do is you randomly turn off nodes throughout the network so that the network doesn't become over-dependent on any specific feature activation. The downside to dropout is sometimes if you have a certain feature activation in the network that's just overly important to the overall goal of the network, it will sometimes train multiple copies of that feature node. So you'll find you have multiple sets of the exact same weights with the exact same activation repeated in your network. So you're basically losing valuable nodes that could have been trained for different things. Dropout's made a lot of headway in certain types of use cases, but it definitely doesn't work for all of them. Some of the variables that you're going to really need to consider, though, are the number of layers that you're going to use and how many outputs each one of those layers is going to have. You also might want to consider biasing per layer or per node. Bias is basically just sort of a background variable that's fed into each layer as sort of a floor or ceiling value. And we'll talk about that a little bit later. Other things that you're going to need to determine is what your learning rate and duration should be. How much, or if you're going to anneal your learning rate, which basically means decrease it over time during training. What, if any max number of epochs you want to run for. An epoch is basically each time you've trained through your entire training set, that's going to be one epoch. You might want to train for multiple epochs to get the most out of your training, or some variable number of those. You also might want to consider early outs. Do we want to possibly cut our training short if we reach a certain accuracy, or if our learning rate anneals below a certain value or something like that? So getting into the math behind forward propagation is actually fairly simple. You'll find, if you look at the bottom of this slide, if you're not used to dealing with a lot of Greek numbers or Greek variables in your equations, something like this can look a little daunting at first. And I've tried to boil this down to the simplest diagram I can for a single node in a neural network. So I'm just going to run through this hopefully fairly quickly. So you're going to have some set of inputs and some set of weights for each layer. So on your input layer, your inputs will just be your inputs. On your next layer, the inputs will be the outputs of the previous layer. Generally, what you're going to have happen here is you're going to multiply your inputs as a matrix multiplication by your weights, which then also includes, as part of the matrix multiplication, summing those weights together. That's going to give you your output value for this node. Sometimes you'll see that referred to as Z or X. It's pretty interchangeable there. Some don't even label that step at all. You're then going to add your bias to that value, whether that's for the whole layer, one value, or individually for the nodes. It'll get added in here. You're then going to feed that value into what's called an activation function. The activation function is something that's selected based on sort of whatever works best for your network. You might get, there's a lot of papers I've seen written on why certain activation functions are better than others for certain things. I tend to have a favorite in tanh right now, but a lot of people still like sigmoid, which was popular before tanh became more popular. And rectilinear activations are super popular right now, mostly in convolutional networks. In any case, you have the sigmoid function, you have tanh, which is the hyperbolic tangent, and you have rectilinear. And rectilinear you'll also see referred to as ReLU, and it basically just means clamp it to greater than or equal to 0. You also see leaky ReLU, which will just change 0 out for a very small value, like 0.00001. So basically, you take the value you've gotten at this point after you added your bias, and you run it either through a sigmoid function, your hyperbolic tangent, or you just clamp it greater than or equal to 0, which just means if it's less than 0, use the 0 instead. So this is where we get our math from at the bottom here. We've got our inputs multiplied by theta, which is our weights. We add in our bias, and we feed that into, in this example, the sigmoid activation function. And that gives us our activation, or output, depending on what layer we're in. Once we've gone all the way through the network, repeating that for each layer, we're going to have our output at the end. We're then going to take our output and compare that against what I like to call our truth. So in other words, in our housing example, if the final value it spit out at the end was $200,000, but our house was actually $150,000 when it sold, our error was plus $50,000. If it was actually $250,000 when it sold, then our error would have been minus $50,000. So in this case, we're just going to take our output minus our truth, and that's our error. Then we're going to take and multiply the activation function derivative into that error for that final layer. In this case, I've provided the derivatives for the most common activation functions here, but if you're using something else, or you just like to find out more about how these work, all of these are easily Googleable. You can find them on Wolfram Alpha or discussions on Stack Overflow, a lot of different places online. So the derivative of the sigmoid activation function is going to be your activation multiplied by 1 minus your activation. For hyperbolic tangent, it's just going to be 1 minus the square of your activation. And for rectilinear, you're just going to take whatever your error was, and if the z of that layer which if you're using rectilinear, it's easiest to just cache the z's as you do your forward propagation. If the z was greater than 0, use the error. If it was less than 0, use 0. If you're using leaky rectilinear, go ahead and use whatever your bottom with your leaky was. So for the output layer, our error that we're going to back propagate back, and we're going to use lowercase delta here for the partial derivative. The full derivative would be the whole network. We're going to use the partial derivative equals the error multiplied by the derivative of the activation function. In this case, the example is the sigmoid, so we're going to use sigmoid prime of z, which is going to be equal to a times 1 minus a. So once we've done the output layer, we're going to go back a layer and do the next hidden layer, and so on and so on and so on, all the way back to the beginning. So for the next hidden layer, which would be layer n, we just came from n plus 1. So as we walk backwards, we're going to go from n plus 1 to n, and then n plus 1 to n, all the way back. So for the lowercase delta here, or error, the backpropagated error for layer n, we're going to take the backpropagated error from the next layer, which we just calculated, multiplied by the transpose of its weights, so transpose theta, and then we're going to multiply in the derivative of the activation for this layer. And we're just going to keep repeating that over and over, all the way back to the inputs. Once we have all those, and you can also just stop at each layer and do this as you go along as well, we're going to find the gradients of each one of those layers, and that's what we're going to use for our gradient descent for our training. So this is a little upside down delta here. It's called a nabla. So we're going to take we're just going to call it the gradient because it's easier. So we have the first one we want to get here is the gradient of our weights. So the gradient of the weights for layer n is going to be equal to the inputs of layer n multiplied by the transpose of the error of n plus 1. So in the case of your output layer, that's going to be the inputs of your output layer multiplied by the error itself. Then you're going to figure out this, and for the next layer, you're going to use this with its inputs, and then you're going to go back and you'll use your next one you figured out for the next one, so on and so forth, all the way back. For your biases, the bias of each layer is just going to be the sum of the errors of the next layer or previous, depending on which way you're thinking about things. And so that's pretty much the entire mechanism to figure out all your gradients. That's how backpropagation works. So the backpropagation is going to get you all your gradients for the weights and biases going through your network, which that's going to let you use gradient descent to figure out how to train your network. So gradient descent is pretty much the main mechanism for how we train neural networks. Gradient descent can be done in several different flavors here. Basically, the best in terms of just sheer effectiveness of training is going to be batch gradient descent. Batch gradient descent is where you take, for your inputs, the entire training set that you're planning on training with, and you just throw the whole thing in there. You get the gradient of the entire training set at once, and you just do an iteration of your gradient descent with that. So every single iteration of your training is an entire epoch. And obviously that's going to give you some pretty good results, because if you have any outlier data in there, it should get overwhelmed by all the good data in there. If you have any noise to your signal, it should smooth that a lot better. Mini batch basically is going to be going through your data set and chunking it up into random subsets of that set and training it one chunk at a time until you've trained the whole set. Then you shuffle it and you do it again for the next epoch. Mini batch is in many ways almost as good as batch, because again you're going to have a sort of group of data so that any outliers can sort of get squashed down. Unfortunately, if you have a lot of outliers or a high noise to signal ratio in your data, you can get some mini batches, which is just going to be one big block of outliers or noise, and you basically end up with a wasted iteration, or in some cases a misused iteration, because you could actually be training in the wrong direction there. With stochastic gradient descent, which you'll sometimes see as called online gradient descent, because it's used in a lot of online applications, or basically applications in progress. You're basically just going to be training with one example at a time. And again, just like mini batch, if that one example you're training with on this iteration is a bad example, you're going to be training in the wrong direction for that example. And if you have a lot of them bad examples in a row, that could be pretty bad in some cases. So there's ways to mitigate for some of that, but you can't get rid of it entirely. You'll also see conjugate gradient descent. Conjugate gradient descent is sort of viewed in a lot of places as sort of a much more complex way of doing gradient descent, which basically it is more complex, but it's not really as complex as a lot of places give it credit for, I think. I found some really, really good resources for learning conjugate gradient descent when I did my project, and I was able to put it together without too much trouble, and I'm not exactly a math major, so I don't think it's really too far off the deep end. If you're looking for something that's a little bit more challenging and might give you a little bit more better results in certain situations, I definitely encourage you to give it a shot. That being said, you also have a lot of adaptive methods for using any of these. There's a lot of methods you can look up, like there's one called Atom, Adagrad, a bunch of other ones. But the simplest adaptive method for gradient descent is just using what's called momentum. So basically, the way gradient descent works is for each iteration of your training, you figure out the gradient of your network using backpropagation. You then take that gradient, and that gradient is basically going to be pointing towards the local minima of your network. That local minima, like any other graphed function, should be the solution to your network, or in any case, the best trained result you're going to get from your network, because what you're trying to do here is minimize the error, which sounds a lot very intuitive, and it is basically. Basically, as you train your network and you throw different problems at it, it's going to have a certain level of error. Obviously, the more error, the worse the result. We want less error. The gradient points in the direction of less error. So you're basically going to take your gradient, scale it by some learning rate. Usually you're going to have something like 10% or 1%, and then modify all of those values by that scaled gradient. So in an example here, if you had one of your weights in your network that was 0.5, and the gradient for that weight, once you figured it out with backpropagation, was 0.5, then you would scale that by your 1%, so you'd get 0.005, and you'd add that to the existing weight. So you'd end up with 0.505 for that weight. And you basically do that with, you figure out the entire gradient, you modify the whole thing, and you add it back to your weights. And that's one iteration of your training. With momentum, instead of adding that directly to your weights, you add it to a velocity variable that you keep track of as you go. So your velocity will usually start out just all zeros. So you figure out your gradient, you scale it, and you add it to your velocity. So for the first iteration, it's exactly the same as any other method. For the next iteration, you take your velocity and you leak a little bit of it out. So let's say we multiply it by 90%, and then you add the new gradient in. So now you're taking and just adjusting the direction that you're training very gradually over time, so that for things like stochastic gradient descent, where each example is only really giving you an approximation of what the overall data might look like, and it might even be a bad approximation, it sort of minimizes the risk of each iteration of the network. Mini batch doesn't need momentum quite as much, especially if you're using fairly large batches. And for batch gradient descent, momentum probably won't be necessary. But it's definitely recommended for stochastic gradient descent. And you can tweak with the values of, how much momentum you want in there, what your learning rates are. There's a lot of interesting ways to go about that. And there's a lot of discussions you can find online about the proper way of annealing and fixing your learning rates and your momentum variables and stuff like that. Generally speaking, though, all of these adjustments are to avoid one of two things, which is either going to be overfitting or underfitting. Underfitting is when you say, if you look at the graphics that I have here, say we have a set of data points that look generally like this. We've got this kind of approximate curve here. An underfit trained network, if we graphed its predictions, might end up looking like this. It does sort of generally follow the data. It is sort of trending upwards, but it's not a very good approximation of the data. There's a lot of error here still. And if you look at something like these graphs, an underfit is probably going to look something like this, where sorry, I should probably explain these graphs first. These graphs are something that is very useful when you're determining the beginning architecture of your network and your meta variables, where you basically take a very small set of your training set to begin with. And generally what you're going to do is you're going to split your data into a training and a cross-validation set. So your cross-validation set is just a certain batch of your data that you're going to set aside, and you're only going to test with that. You're not going to train with that. And the reason that you do that is because you want to approximate the performance of your network on data that it hasn't seen before during training. So I think you'll usually see these broken up either 60-40 or 70-30, 80-20, something like that. So basically what you're going to do here is the first thing you're going to do is you train your network on just a very small subset of your training set, and then validate it against your cross-validation set, the whole thing. Then you're going to do it against a little bit more, and a little bit more, and a little bit more, and this will show you approximately how well your trained network will train over time given larger and larger and larger sets of data. So in this case, it looks like they went from 0 to 100 training cases, which for most networks, that's not going to take very long at all. I mean, it probably only took them a couple minutes to generate this graph, and if they're on a really strong computer, probably even less than that. So in this case, you can see the training set, its error went very, very high up here very quickly based on this dotted line is their basic benchmark for where they want to be error-wise. So it shot up over where they wanted to be very quickly and stayed there. It's going to start off fairly good here, but it's going to go up pretty quick. So if you see where basically they're underfit here, you can see that pretty much every example here isn't on the line. This is going to be a fairly high rate of error, even though it's a pretty decent approximation of the data in a very broad sense. And you can see the cross-validation error also came back to pretty much in line with their training data very quickly. The only problem is the overall error is still reasonably high, and it's not really coming down anymore. This sort of graph is going to tell you that you're underfitting your data. If you're underfitting your data, things that you might want to consider doing is building in more variables. So if you're doing the house example, collect more data on your houses and feed more data to the network. It'll give it a little bit more ability to hopefully meet the right curve that you're trying to get there. Other things that you could do is you might be normalizing your network too hard if you've built normalization in, so you might want to try and scale that variable back. And then you have overfitting. Overfitting is where you've built in all these variables and you have maybe not enough normalization, and you're building all this super strong power into your network to just really super fit your data. And you can see this line goes through every point right immediately directly through its middle. But this is a crazy graph. Like if we're talking about like housing costs here, obviously this house that has like negatives for all of its values isn't going to be up here. And this house that should be in the mid-range of your prices here suddenly takes a weird dip. And that's because you're getting this really super weird polynomial equation here. And it's meeting every single thing in your training set here. But obviously once we start adding in that cross-validation set, you're going to have a point here and a point here. It's going to be off for all of those. So you can see what this graph looks like. It's going to look like, oh, look, our training set basically learned up pretty quick. And it's staying pretty low, and it might even continue going down here. But our cross-validation sets stayed really super high error for a long period of time, and maybe you'll see a couple of jumps downward, and it might even go back up. But you're gonna keep a pretty good gap here, and your cross-validation will generally stay higher than you want it to be, even if your training set stays really low. And kind of in my experience, one of the big indicators of overfitting is if your training set immediately hits a super high accuracy rate. That's, I mean, it'd be really great if that happens, but it's not very realistic. So that's probably a sign your data set's being overfit there. And obviously, once you get away from having either extreme, you're not normalizing too hard, you've got a decent number of variables, but not every variable ever, you're going to get this sort of curve that fits in here pretty good. And what you're going to see here is your training error is going to come up and meet a pretty good accuracy here, and then it slowly go down over time. And your cross-validation error will be pretty much a mirror of that. It's going to come down fairly quickly and meet or get very close to that green line, and then they're both going to sort of go down together in lockstep. So that's what you're looking for. So with the convolutional neural networks, we're going to take everything we just learned, and we're going to apply it to a new type of problem. So we're going to talk about what the use cases for this new type of neural network is. And one of the biggest problems I ran into with convolutional neural networks is there's a lot of confusing terminology around them and a lot of terms that different researchers or different projects use to mean the same thing when they might be different, or they use different terms to mean the same thing. So we're going to go over some of that confusing terminology. And then again, we're going to go over the general mechanisms of how these actually work. How do you put them together and implement them? So the use cases for convolutional neural networks is they were originally designed to sort of, again, this was inspired biology, and it was to sort of approximate how the retina and the visual cortex of the brain deals with imagery. So basically in this case, the retina is almost like a bitmap. You've basically got this big field of receptors, and it's all being fed into neurons like a neural network, and basically fed through a bunch of different layers. So the idea here was to sort of approximate a neural network with sort of a bitmap style data representation. And the idea behind this was to use it for image recognition. And so because we're using image recognition here, we're going to go through images and we're going to basically try to perform classification on them with our convolutional neural network. We're going to pick out, oh, is this an orange, or is it a banana? Is this a cat, or is it an Xbox? What are we looking at? One interesting thing about that here is it's easy to train a convolutional neural network that'll tell you what the image is, or it's easy to train a convolutional neural network where you say, hey, show me where the cat in this picture is. But it's very hard to make it do both at once. It's basically not possible. You can tell it, show me where the cat is, or you can tell it, tell me if this is a cat, or tell me what exists here, and it'll be like, that's a cat. But it's hard to tell the neural network to say, what is in this image, and once you've told me what it is, tell me where it is. So you basically need two neural networks trained slightly differently for that sort of output. Another thing that you can use convolutional neural networks for is just feature extraction. So maybe you have another just regular neural network that you're trying to use for a certain thing, and one of the inputs you want to input into it would be a picture of something, or even a sort of data that has sort of spatial data like this that might not be a picture. Other things you'll see convolutional neural networks used for is like an audio signal, because again, audio signal has this sort of ordered sort of map of data. So you can almost think of it as sort of like a 1D bitmap. Also text, you'll sometimes see people will break text down into a dictionary. So like each word is represented by a value, and then you have this string of values. Again, it's sort of at that point like a 1D bitmap, and you can use a convolutional neural network for that as well. And you can use this to extract your features to feed into your regular neural network. So you basically feed this bitmap in, and you say, tell me what's here. And it says, in this case, it'd say banana, orange, 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 orange. And so that's your data that you're going to feed into your regular neural network, and you're going to figure out something about bananas and oranges. Maybe what is the overall price of this fruit bowl? And it'll say, well, it's 4 oranges and a banana, so I know the price now. And the interesting thing about these convolutional neural networks, because of the way they work, is they're location invariant. So as long as it can identify a cat, and there's a cat someplace in this image, it should be able to identify cat no matter where cat is. So it could be here, It could be here, it could be here, it could be here, it doesn't matter. Whereas on a regular neural network, if I feed a bunch of bitmaps and I train a neural network to identify cats in this location, it won't be able to recognize that same cat if it's up here, whereas a convolutional neural network would be able to. So on to that confusing terminology. Again, this was one of my biggest stumbling blocks with dealing with convolutional neural networks. So you're going to see people refer to features, feature maps, channels, dimensions, activations, hidden layers, filters, kernels, and 2D versus 2D batches, 3D versus 3D batches, and 4D or even 4D tensors. So a feature, sort of the best, most often agreed upon definition of a feature here, is when you do convolutions in the network, you're going to be applying filters to your image. So if you think about these as nodes in the previous example, each one of your nodes has an activation on the next layer. So the feature is the activation of your filter being applied to the image. So in this case, super layman's terms here, let's say we have a cat filter and we have a certain activation level. So that's the cat feature now. So we take the picture, we apply our cat filter, we have an activation, that activation is our cat feature. Once we take that whole layer and we have all those different nodes, maybe we've got a cat, a dog, a car, a building, a person, and we take all those and couple them together into one multi-channel bitmap for the next input layer. That's our feature map. So it's all of our features into a multi-channel input for the next layer. That's a feature map. And again, I mentioned channels already. So in a standard RGB bitmap, you have 3 channels. You have red, green, and blue. You feed that in with your filters, your next hidden layer, now you're going to have all those features. So instead of red, green, blue, now you've got cat, dog, bird, plane, car, and those are your channels now. You'll see dimensions here as well. I mentioned this previously when I was talking about signals, like audio signals. That would be a 1D input. Or you might have a 2D bitmap, or you might even have something more complex than that. And for example, the audio signal probably only has 1 channel, or it might be left and right audio, in which case now you have 2 channels. And with the bitmap, you probably have red, green, blue, maybe alpha, so 3 or 4 channels. Activations is basically the same terminology we've been using before, but some people will use it a little bit differently, depending on whether they're talking about an individual pixel as an activation or the entire feature as one activation. Hidden layers is basically used the same here. But again, once all these terminologies sort of start coalescing, when people start talking about convolutional neural networks, it can get sort of a bit difficult to pry it apart. So I just wanted to sort of say that hidden layers here basically refers to the same thing. And those hidden layers could be hidden layers of filters. It could be a hidden layer of an actual standard neural net that it's feeding into. But either way, if it's not the input and it's not the output, it's hidden. So the filters here are your set of weights that you're applying to each image, and they're applied in a very particular way, which is what makes this a convolutional neural network. And when we get to the mechanism in a couple slides, you'll see why. A kernel here can either refer to a single filter or a set of filters. And if we're talking about a set of filters, we're basically talking about all the filters we're using for one layer. So that could be referred to as a kernel, or they could just be referring to one of your filters. So 2D versus 2D batch versus 3D versus 3D batch versus 4D tensors. So when you're looking at the set of filters or kernels that you're using for one of your layers, if you have a 2D image that's only one channel, your filter is going to be 2D. However, if you have multiple channels, again RGB with 3 channels, that can either be referred to as a 2D batch or as a 3D filter, because you're going to have, height and width and then 3 channels, so you have a sort of a depth there. Then you might have multiple filters in that layer, which you probably will. So you can either see that now as a 3D batch, or some people will refer to that as a 4D tensor. And it really just depends on what neural net framework you're working with. I've seen these used different ways in Caffe and TensorFlow, and I built my own network topology and array fire. So there doesn't really seem to be a lot of consensus on which of these to use. Just sort of, in this case, the best thing to do is just sort of read carefully and try and figure out what the author is trying to get across here. So the general mechanism for a convolutional neural network is actually not convolution, strangely enough. It's correlation. Convolution and correlation is identical, except for the fact that in convolution, you take the filter and you flip it vertically and horizontally before you apply it. In a convolutional neural network, that is usually not the case. They're usually just applied directly, which is referred to as correlation. One big difference you're going to see between different convolutional neural networks in terms of a metavariable is whether or not the inputs are padded before being sent through. And we'll explain a little bit more about that later. One thing, convolutional neural networks are translation invariant, meaning no matter where in the image that thing you're trying to look for is, should be able to find it. However, they are not scale or rotation invariant. So if we have a cat that we've learned to recognize in our image and it's here, we'll find it. If it's here, we'll find it. If it's here, we'll find it. But if it's here and twice as big, we might not find it. If it's here but it's upside down, again, we might not find it. Some of the ways around this are just to train additional features so that maybe, we recognize a cat's head that's pointing straight ahead, as well as one that's upside down or sideways or slightly bigger. Other convolutional neural networks will simply feed the image in several different scales and check against each one. Channels in versus channels out. So again, we were talking about if you had a bitmap, a 2D image with 3 channels, R, G, and B. Generally for each layer, you're going to want your filter to spit out a single channel, but take in multiple channels. So your filter for the first layer should take in all 3 channels of the bitmap and spit out a single channel, because that's going to be one activation set, one feature. And then you're going to take all your acquired features from that input, from all your different filters, and stack them up as channels into one input to the next layer. And then basically forward propagation and back propagation are still going to be the mechanisms that we're going to be using. It is still a neural network after all. So padding and convolution type. This is something, it's not necessarily one of the complicated parts of this, but it is something that will trip you up fairly often. So padding can either be zero padding or extending the border of your image. So if this square here is your image, and let's say this little square is your image right here, and we need to pad this out to apply a convolution. So we're padding it out to here. We can either just set all of these pixels to be zeros, like just add some black space out here, just basically a mat around your picture. Or we can extend the border, like say these 3 pixels were blue and these 2 were green. Well, we can just extend that out so all these are green and everything out here is blue. And depending on specifically what you're trying to train your network for or what your results have been in the past, you might want to consider one or the other of these. It's really going to depend on your individual case. For the convolution type, the 3 that I've seen used the most is what's normally referred to as valid, full, or expanded, and that's what this picture here is going to illustrate. So a valid convolution is where you take your filter and you apply it throughout your image only where it doesn't overlap the edge of the image at all. So you apply to the edge but not past. A full convolution is going to be applying the filter anywhere where the center of the filter doesn't go off the edge of the image. So in this case, you're going to need to consider what type of padding you're using. An expanded convolution is where you're applying your filter anywhere where any portion of your filter overlaps any portion of the image. So you're going to need a lot more padding here, and you're going to end up with a much bigger output. You'll also see sometimes same convolutions, which I've mainly seen in MATLAB, which basically just means we're only going to produce an output that's the exact same size as the input image. So regardless of which of these other types, I believe the same uses a full convolution, but then it truncates the size of the output based on the size of the input. I haven't really found many uses for same. I'd probably just avoid it most of the time. Okay, so we're extending our diagram from earlier a little bit to demonstrate a neural or a convolutional neural network now. So we're going to have our input here. In this case, we've got our RGB input, and we're going to have several filters. Filters for each layer are generally fairly small. Even if you're working for a pretty decently sized bitmap, let's say we're just doing thumbnails, 128 by 128 pixels with 3 colors. Our filters are probably only going to be maybe 3 to 5 pixels on a side, so 3 by 3 or 5 by 5, and again, 3 channels. And basically, the way a convolution works is you apply the filter, and it's basically a weights matrix. So you overlay the filter on top of the image, and you multiply all the inputs by the weights that overlap them, and you add them all together, and that becomes a pixel on the output. And then you move it, whatever your stride is. You're usually going to see it as a stride of 1, but sometimes you'll see a larger stride, like maybe you move it 2 pixels at a time, and you do it again. And you just keep doing that all the way across. If you know anything about graphics programming, you've probably seen something very similar to this in terms of edge finding algorithms, Gaussian blurs, all sorts of things like that. So this shouldn't be something totally new to you. And again, because we want to keep the number of channels in our filter the same as our input, there's not going to be any room to move that filter forward and backwards, so the output should only be 1 pixel deep. So we're going to have each one of these features that comes from convolution, or actually correlation, with this filter. We're then going to stack all these features up into a feature map, which then, hey look, we've got a multi-channel bitmap again. We feed that into another hidden layer of filters all the way down until usually what's going to happen is you're usually going to get down to the point where each one of your outputs is a single pixel, either by convoluting it down and losing some because you're not padding each convolution until it just becomes a single pixel, or because you'll do something called a pooling layer. And that pooling layer is basically just a downsample. So you're just going to take and either use a max pool, which is let's say we're doing a 2 by 2 max pool. So for each 2 by 2 section of pixels, we just take whatever the maximum value is, we discard the rest. So you're going to basically half the size of your image every time you do a 2 by 2 pool. Or you could do a 4 by 4 and quarter the size of your image. A mean pool would just be taking those pixels and taking the average and using that value. Most convolutional layers use pooling simply just to reduce the size of the inputs to each subsequent layer. Usually max pool is used, but sometimes you'll want to use mean depending on your particular use case. And you will lose some training fidelity, but usually not as much as you think you would. And it helps you very much cut down on the cost of training and calculation in your network, because there's much less data moving through the network from layer to layer. Also, pooling layers are much less computationally expensive than a convolutional layer. So anyway, you're going to get to a point here where you're basically down to single pixels for each one of your features. So basically, each one of those features that you've gotten at that layer is at this point just an activation. So we figured out some high-level feature and determined how much of it exists in this image. You will usually then feed those into a neural network and end up with some sort of output. Because these are used for classification a lot, you'll see a particular type of classification output that's used called a softmax output. I'm not going to go through all the math that goes behind a softmax layer because it's not particularly salient to understanding this right now. But just understand all the softmax layer does is it takes all the activations on the output layer and makes it so that they all add up to 1. So it makes basically a statistical distribution out of your output layer. So there's 100% that your chance that your output is something, but we're going to distribute that chance between all the different possible somethings it could be. And then basically you'll take whatever your maximum activated feature is, and that's the one you determine to be correct. Or if there's none of them that are above a certain threshold, you might just say the network didn't know. Again, there's also going to be bias here probably built into each convolutional layer at least, and there's going to be an activation onto each one. And then we're going to back propagate. Obviously, the math going forward and backwards is going to be a little bit different than we were doing before, but once we get to the neural network portion of this, it's going to be obviously exactly the same. Okay, so with forward propagation here, forward propagation is pretty much just going to be the forward propagation based on the convolution. So you'll be doing a convolution, possibly adding a bias, and then using an activation layer. Then you might throw in a pooling layer and do it again all the way down to the neural network layer at the end. For the back propagation, though, that's where things get a little bit mixed up. First thing you're going to need to figure out, because it'll probably be the first layer you encounter on your way back through the network, that's going to be a new thing that you've seen, is going to be your pooling layer. So if you're using a max pooling layer, basically you're going to keep track of which pixel you selected from to max, and you're going to cache those values. So when you come back through, you're simply going to tile the error based on the selected input. So if you had this 4x4 area that became this 1 pixel, whatever that error is that corresponds to that pixel is now going to go to just the one that was the max. So if this one was the max and that became this new pixel, or if this one was the max and this became this new pixel, you're just going to put that error right back where it came from. The rest of them will all be 0. If you're using a mean pool, you're basically taking the average out of the whole thing, giving one output value. So when that error comes back through, you're going to take that one error value and just tile it over the whole thing, because they all equally contributed, so they all equally share in the error. After this point, you're basically going to take the error that you've been back propagating, and you're actually going to convolve it this time with the weights. And the weights in this case are the filters. So you're going to take the error that's coming back through, and you're going to, this step is correlation. The gradient is convolution. So you're going to correlate. So you're going to take your error, and you're going to pass your filter over it in a correlation again, and that's going to give you your back propagated error, your partial derivative. This should be run as an expanding correlation. So if you remember back when we talked about the expanding here, where you're basically taking anything that even partially overlaps. So in this case, your output from this correlation should be bigger than your inputs, which, if you remember, your inputs are going to get smaller as you go forward. They'll be getting bigger as you go backwards. Then you're going to need to, for each one of those layers, you're going to need to calculate the gradients for your filters so that your filters can be updated, which that is how your network learns. And you're going to still just be using the same gradient descent methods that we learned before. They're just going to be applied to all the pixels in your filters as if they were weights in a matrix. And you'll probably be storing them in matrices anyway, so it's all going to be basically the same algorithm. In this case, the gradient for that set of weights is going to be equal to the inputs of that layer, in this case actually convolved with the error that you're back propagating. So you're going to take your inputs, you're going to take that error, you're going to flip that error vertically, you're going to flip it horizontally, then you're going to convolve it with an expanded convolution, and that should match the size, you might need to trim a little bit, of the filter weights that you have. And that gradient will be used once you've figured out the entire gradient for your gradient descent iteration. If you used an activation function, instead of just doing this step here when you're back propagating the error, you're going to also multiply in the derivative of your activation function. So again, if you're using sigmoid, as we have in this example, you're just going to be doing your sigmoid prime, which the equation for that was on a previous slide. It's your activation multiplied by 1 minus your activation. So that'll just be multiplied into your back propagated error. Pretty simple. So one thing that you can use to make this a lot less complex when you're setting it up in your actual implementation is to, both for the regular neural networks and for the convolutional neural networks, separate your activations and your biases into their own layers. So in this case, for your forward propagation here, your weights layer is just going to be your inputs times your weights. This is going to be a matrix multiply, and that's going to be your output. Then you're going to feed that to your bias layer. So that output becomes your new input. You add your bias, that's your output. Then you're going to have an activation layer. You take that output, becomes your new input, feed it into your activation function. In this case, we're using sigmoid, and that becomes your new output. Then when you're coming back through the network, for your backpropagating the error through your activation layer, so again, now we're going back up because we're going backwards. Your backpropagated error coming out of this layer is going to be the error that came into this layer times the derivative of your activation layer. So for the sigmoid, derivative of the input for this layer. Then you're going to take that and backpropagate it through your bias layer. Your bias layer, it doesn't change the error when it backpropagates through. It'll just come straight through. For your weights layer, again, it's going to be the backpropagated error times the weights, and that'll be the error that continues to backpropagate through. So it's very easy to do this in a step-by-step fashion, both forward and backwards. To figure out the gradients, activations don't actually have a gradient. There's no weights that you're feeding into sigmoid. It does the same thing every time. For your bias gradient, so you just not calculate a gradient for this. For this one, when you get your bias layer here, you would just take that error that you fed in, just sum it. That's the gradient for your bias. Then you'd pass this back into your weights layer. Your weights layer's gradient is going to be the inputs multiplied by the back propagated error transposed, and that'll be your gradient for your weights. So again, just step by step forward, step by step backwards. It's all very separable, so you can really break it down into individual pieces, and it makes it much easier to implement. And that's pretty much the whole thing. I hope that's been a little bit easier to get through for you than it was for me. A lot of this is sort of scattered all over the place through different tutorials and isn't really able to be digested in one chunk like I've hopefully been able to give you. So, thank you for your time.